Welcome, hello students, and welcome to the lesson. So today I want us to look at the last part of our topic. That's the rate of reaction and the reversible reactions. I want us to look at some of the industrial applications that use that knowledge that we've been learning in the topic. Our first process, we're going to look at the HABER process, which involves production of ammonia gas, and we're going to see how temperature, pressure, and the catalyst and the concentration, how those factors were considered in setting up the setup or coming up with the optimum conditions for the HABER process. So we're going to start with the first one, change in temperature. So the optimum temperature used or ensured or maintained in the system is about 450 degrees Celsius. So as you can see, the forward reaction is exothermic. That's why the enthalpy change is negative here, meaning the process is producing some heat. So we expect that reducing the temperature will favor the forward reaction. However, in the HABER process, they use 450 degrees Celsius. Why? So lowering the temperature will favor the forward reaction. However, the rate of the production of our gas here will be so slow. It is going to take several days to produce a significant amount of ammonia, which is not economical. So that's why they use the compromising temperature of 450 degrees Celsius just to make the process a bit faster, because time is a factor in any business. Next, we're going to look at the pressure. So the optimum pressure used in the HABER process is 200 atmospheres. So as you can see, my equation is not balanced, sorry. So this is 3, should be 3, and here we have 2. So that there we have 2. So as you can see, we have 3 moles here and 2 moles here. No, here it should be 1. So we have 3 moles here and 1 mole of nitrogen. So in short, on the reactant side we have 4 moles, but on the product side we have 2 moles. So increasing the pressure will favor the forward reaction, which is going to make a shift on the position of the equilibrium towards the right, because the reactants are more bulky than the product. So that's why they are using higher temperature. So using higher pressure rather. So using pressure higher than 200 will increase the rate of production of ammonia. However, it will require you to use very expensive equipment which will be able to accommodate such higher temperature. Then catalyst. So we have 2 catalysts that are used in the HABER process. We have the iron and we have the platinum. So iron is preferred more than the platinum because iron is less expensive. Iron is not expensive. I don't know whether that's the right English. Less expensive compared to platinum. Again, iron does not get poisoned. Does not get poisoned by impurities compared to platinum. Then another factor that is used to ensure that the forward reaction is always favored is by constantly removing the ammonia gas from the system. So immediately the ammonia gas is prepared, then it is immediately removed from the system. So the forward reaction must always proceed to produce more ammonia. So our next process that I want us to consider is the HABER process. No, the contact process. Contact process. So under the contact process, we're still going to consider our factors here and see how they are. So in the contact process, that is the production of sulfuric acid. So the most important equation there is the conversion of sulfur 4 oxide or the oxidation of sulfur 4 oxide to give us sulfur SO3 sulfur 6 oxide. Let's balance. So here we have 2, 2, 6. Yeah, that's our equation. Oxygen 4, no, yeah, and the enthalpy change here is negative 197 kilojoules per mole. So let's start with the temperature. As you can see, the reaction is exothermic. So lowering the temperature will favor the production of sulfur 6 oxide. However, the optimum temperature used in that process is 450 degrees Celsius, an average of about 450, for the same reason, to increase the rate of reaction. Then pressure, in this one, the pressure used is between 1 to 2 atmospheres. Let's look how many moles we have on the reactant side. So here we have 2 and here we have 1, so that's 3 moles. And again, on the product side we have 2 moles. So increasing pressure therefore will favor the production of our sulfur 6 oxide. So that's why the pressure used in that system is between 1 to 2 atmospheres. If you use more pressure beyond 2 atmospheres, the rate of reaction, you will not be able to produce sulfur 6 oxide gas, because at high pressure that gas will liquidify, and that's why the optimum temperature must be used between 1 to 2 to ensure that we get our products in gaseous form. Then the catalyst used in the contact process, we normally use the vanadium 5 oxide. So the catalyst is just to ensure that it fastens the rate of reaction. And finally, the concentration of sulfur, the concentration in this contact process, excess oxygen is always used to ensure that the forward reaction will keep on progressing. So they use excess air. So in there, of course, we know in air we have the oxygen. So that is to ensure that the forward reaction progresses. So that marks the end of our topic, and meet you soon. Thank you.